Hello learners, today we are going to learn about sets. So what comes to your mind when you hear about sets? What it is basically? So it is a collection, right? If you have, say you are collecting all the alphabet, or maybe you are collecting the numbers, maybe you are collecting any objects. So whatever it is, so these are all sets. That means set is basically a collection, right? So how do we define it mathematically? So a set is a well-defined collection of objects. We'll come to this point why we are telling it as well-defined. But first, let's see examples. So suppose if I collect, say, numbers from 1 to 10. I am putting inside a set, say 1, 2, 3, 4, 5, 6, up to 10. I'm collecting these numbers. You can see here we are writing the objects or whatever we are collecting inside parenthesis, that is brackets, flower brackets in normally how we call this. So a set is written in this form. We are separating its elements using commas. Usually, we denote set by capital letters and suppose its objects are to be named, we normally name it by small letters. We can also write set as, say suppose I am taking one more set. We are collecting the numbers. Which numbers? Natural numbers. We know that natural number is denoted by n. So we are collecting the numbers in naturals. How we are collecting? In between 2 to 20. So this is one more form of writing a set. So here we are explicitly writing the elements. Here we are describing the element's nature. Okay. Suppose if I am collecting all the natural numbers for the infinite set, we just put this dots. This denotes a set is infinite. So you can see that set A is finite, set B is also finite, natural number set is infinite. So, is there any possibility that there is no element in a set? Yes, we call it as empty set. And empty set is denoted by just two flower brackets, nothing inside the set. This denotes empty set. Empty set means there is no element in the set. Otherwise, we denote it by letter phi. Some call it as phi or else phi, whatever. This is the notation. Now we will come back to the point well-definedness. Why this word is important? Now, suppose if I say collect all the natural numbers, you will naturally give me this set. Or suppose if I ask you collect all the integers, you will give me this particular set, right? Set containing all the integers. This is uniform everywhere. That means even if one student is writing this set, it will be same. One more student is writing, it will be same. Whoever is writing the set of integers remains the same. Whereas if I give you or if I say you list all famous singers in India. Suppose if I give you, so one person may tell one 10 names, other person may tell some 5 names. So that list will vary from person to person. This will not be same for each person who is listing. So this cannot be a set. There is no well-definedness in famous because this is a very relative word. So whatever aesthetic things are there or which is not giving a particular meaning when we are using, that cannot be used for the definition of set. So hence the well-definedness matters. How to write sets in two types? We have already seen in examples. See here, we are listing the set elements. Here we are describing the elements. So same thing we have here in roster form. We list the elements. In set builder form, we describe the elements. These are just two types to write a set. However, you can use sometimes if a set is small, you can explicitly write the elements. If a set is big, you cannot write all the elements. You cannot list them. So, set builder form will be useful in that case. Suppose if I give examples, so I have a set A. So, what are these elements? I think now you know. This is basically multiples of 3, right? So how can we write it in set builder form? Suppose if I say we are collecting all the natural numbers such that here the colon is used to say such that, or we can also use this symbol instead of this. Okay, now we are collecting the natural numbers such that what is this x? It is a multiple of 3. Multiple of 3, how can we write? We can write it as 3n, where again n belongs to naturals. That means here how we have 3? 3 into 1. How we have 6? 3 into 2. Similarly 12, 3 into 4. So this 1, 2, 4 all are in natural numbers. So we are representing this set compactly as this. You can see these two sets are equal. So suppose if I take one more example, can you guess what numbers I am writing? Exactly, they are the square numbers from 1 to 10. How can you write it in set builder form? So suppose if I write this in set builder form, yes, x belongs to natural numbers such that 1 less than or equal to x square less than or equal to 100. That means the square, we are collecting the natural numbers whose square is in between 1 to 100. That's what we are collecting, right? Similarly, you can convert some set builder to roster form. For example, suppose if I collect the numbers x belongs to natural numbers such that, now can you list this? It is simple. The numbers between 3 and 9. Here we can see that 3 is included but 9 is not. Therefore, we will be writing 3, 4, 5, 6, 7, 8. 9 is not included. Okay. So this way you can convert set builder to roster or roster to set builder. So basically these will be used to represent a set. So whenever the set is given in set builder form, you should be knowing exactly what elements that set is containing. Okay, good. Next, we'll see when two sets are equal. Yeah, one more point to note is that you can see in a set, we are not repeating any element. That means whenever you are collecting the elements or the objects, one element written only once in a set. Suppose if I have a set, so this repetition is not allowed. Basically, this is nothing but we are collecting 1, 2, 3, 4. Okay, now we'll see when the sets are equal. So what do you think when two sets may be equal? Suppose if I have A to be 1, 2, 3, 4, B to be 3, 2, 4, 1. Do you think these sets are equal? Yes, they are equal. Two sets are said to be equal when they have same elements. Okay. So from here you can see that the ordering in the set doesn't matter. We are just collecting the elements. So here also we are collecting 1, 2, 3, 4. Here also basically we are collecting 1, 2, 3, 4. Therefore both sets are equal. Two sets are said to be equal when they have same elements. One more concept is, how do we denote the number of elements in a set? Already we have seen two types of sets, finite sets and infinite sets. Of course, empty set comes under finite set itself. We usually denote number of elements in a set by n of A. So n of A denotes number of elements in a set A. Okay. Otherwise, we also denote it by two straight lines. In the middle, we write the set notation. So this is known as, either we call it as number of elements or there is a explicit wording that is cardinality. So this will be used in higher mathematics, like it's a standard word, that cardinality of a set. It's okay if you don't use it now or if you are not used to it, you can just say number of elements and you can use this notation as well. This notation should not be confused with modulus notation, which we come across. Okay. Now for a finite set, suppose if I say what is the number of elements in this set A, that is 4, right? So we say n of A to be 4, or else cardinality is 4. Okay. Now what about the infinite set? How do we write the number of elements in infinite set? So usually we do not write it explicitly, but you can say that it is infinite. And so here when A is infinite, so n of A will be 0 when A is empty. For an empty set, number of elements in it is 0. Obviously, it doesn't have any elements. Okay, so next we will look into the concept subsets. What is the meaning of subset? So suppose you are given with a set A, say till number 10, 1 to 10 we have collected in set A, and set B is just 1, 2, 3. Now you can see that the elements of B are also the elements of A. That means, suppose if I have a set, if I represent my set A as this big circle, here there are elements 1, 2, 3, 4, so on up to 10, right? You can see that B is sitting inside A, right? B is on its own, it's a set, and it is sitting inside A. That's why we call B to be a subset of A. So how can you write the definition of subset? A set B is said to be subset of a set A if all the elements of B are also the elements of A. Elements of B are also the elements of A. This way we are defining subset. So suppose if I say natural number is a subset of real number, this way we are denoting real numbers. So this will be true. All the natural numbers are also the real numbers. The notation for subset is this. This is basically contained in, we say B is contained in A. When B is a subset of A, we say B is contained in A. So this notation we use for a proper subset. This notation we use, it may be equal to the largest set. That means here we can see B is properly contained in A, properly sitting inside. Then we can use B subset of A, proper subset of A. There is no harm in writing this. This will also go, but if we are very precise, we can use this. So for any set, we say that a set is a subset of itself. So in that case, we can write A is a subset of A, B is a subset of B. So usually this notation we will use when we don't know the exact nature of sets sometimes. Now in the basic concept or initially we don't require that. We can just use this notation everywhere. It's absolutely fine. But when we require some precise notations, we can differentiate into this. So one more thing, can I say empty set? So if you remember, we denote it like this. Empty set is a subset of every set. So empty set will be obviously contained in every set, right? So it's a subset of any set you choose. So when I come to real numbers, you will be denoting a real line like this, right? Okay, if I now write a set, I'm collecting all the elements of real which are lying between -1 to 1. So basically I am collecting these elements, right? Which are here. So how can I write this set now? I can write it in this notation. This notation you may be knowing, this is the interval. Okay. Interval means this is the subset of real numbers. So this set is basically denoting the interval -1 to 1. This is called closed interval because both the endpoints are included. Suppose if I collect only the numbers between -1 to 1, excluding the endpoints, this we will call it as open interval. So similarly, you can have half open, half closed also. So intervals are subsets of real numbers. In the next lecture, we will see what are Venn diagrams and mainly operations of sets. If you have any doubts, put in the comment section. Thanks for watching.